Hello everyone, in this video I would like to discuss everything you need for the lab number 3. For the first part of it, which I would say most time consuming part and much more complicated than the second part of this lab. I'm going to record a video related to Poisson distribution, which you need for the second part of this lab separately. Okay, so for the first part I prepared Excel file where I'm going to discuss a little bit of the theory based on the well-known experiment rolling a die. I'm not going deep into the theory since I assume that you covered everything you need from chapters 4 and 5 of the book and went through all the activities in the course schedule. Okay, so the first definition I would like to introduce is the random variable. And random variable is just numerical description of our outcomes. Yeah, if let's say we are flipping the coin, that's another well-known statistical experiment. So then we can introduce our random variable as 0 and 1. Yeah, so 0, let's say heads, and 1 is tails, or vice versa. Or it could be other numbers. 0 and 1, I think those are just more convenient numbers for the description of the outcomes in this particular case. Okay. In our case, it's just 1, 2, 3, 4, 5, 6. Those are just the values we see on the sides of the die. Okay, and if a random variable can take only a finite number of distinct values, then it must be discrete. Okay, so that's what we are considering in those chapters 4 and 5, discrete probability distribution. Yeah, so let's see what we have here. Yeah, we have that experiment. Yeah, we are rolling a die. In how many times? Let's see. So we are rolling a die. So let's calculate sum of all these numbers right there. So 60 times. Yeah, we are rolling a die 60 times. Okay. And out of the 60, 8 times we get 1, 10 times we get 2, 9 times we get 3, 12 times we get 4, 11 times we get 5, and 10 times we get 6. Okay, so let's introduce definitions of probability, which we are going to use here. Relative frequency approximation of probability. So this is experimental. So this is experimental value. So we take a number of times A occurred, so which is, for example, in case of 1 is 8, and divide by number of times procedure was repeated, which is 60. Okay, and there is a classical approach to probability, which is theoretical value. So that's number of ways A occur divided by number of different simple events. Okay, so in this case, if we are taking 1 again, so in how many ways we can roll 1? In only one. In one case, when we roll 1, yeah, and divided by number of different simple events, so that's 1, 2, 3, 4, 5, 6. So we have 6 different simple events here. So then it's just going to be 1 over 6 in this case, and the probability distribution, which is just the distribution of probabilities, it's going to be uniform, yeah, because theoretically all the probabilities for all simple events, they must be the same, yeah, 1 over 6. Yeah, and what the law of large numbers tells us that the more we roll a die, the more we repeat the procedure, the closer our experimental values are going to be to theoretical. So the closer that a relative frequency approximation of probability is going to be closer to classical approach to probability. Okay. Okay, so let's calculate probabilities in this case. So this is equal to 8 divided by 60. Okay, and let's drop it down. Yeah, and here, if this is the probability distribution, so all this stuff should sum to 1. Okay, we go there. Okay, so it's 1. Okay, and theoretical values. Theoretical values of probabilities. Let's maybe format cell this number. Okay, reasonable. Okay, it just equals to 1 over 6. Okay, and just drop it down. and again, so it should be sum of all these values equals to 1. Okay. Okay, so that's what we have. Yeah, so that's what we have. Yeah, if you don't have 1 here or 1 there, so that means this is not probability distribution. Yeah. So again, make sure also that all those values are positive and less than 1. Yeah, less than 1. Probability cannot be greater than 1. Okay. Okay, so that's what we have in terms of the frequencies and probabilities. We can also go ahead and insert the histogram. Yeah, this is going to be our experimental result of actually rolling a die. So let's maybe move it a little bit like this. Okay, and yeah, if you go here, insert. So quite common error, like to use the histogram. So again, guys, if you have your frequencies, you have your probabilities, that's not where you apply histogram. Histogram you apply it directly to the data set. No, here you just need to use 2D column. Okay, and this is going to be our theoretical. Okay. Okay, so that's what we have. Yeah, let's maybe make it a little bit smaller. Yeah, as you can see, yeah, so the experimental, it's not that uniform. Why? Because we are rolling it just 60 times. If we continue rolling it, roll it 1,000, 2,000, million, billion. So then, yeah, our experimental values will approach theoretical values in terms of the probabilities and other parameters. So such as mean, for example. Yeah, so the mean value. So let's calculate the mean value. So then we are going to calculate variance and standard deviation. Okay, so the mean value, we are going to use the formula for weighted means. We are going to use our probabilities for the outcomes as the weight. Yeah, and we are going to use some product, and those are our x values, and multiplied by the values of probabilities. Okay. Okay, so 3.6, as you can see, it's quite close, and if we actually round it, if we cut the tail, it's going to be 3.6 as shown here. Yeah, for example, if you are talking about theoretical value of the mean. So if, let's say, we are rolling our die 6 times, yeah, so 1, 2, 3, 4, 5, 6, and let's say first time we got 1, second time we got 2, third time we got 3, so then 4, 5, and 6. So then what we need to do, we need to add up those numbers and divide it by the numbers we rolled the die in this case, yeah, by 6. And if you add everything up, 1 plus 2 plus 3 plus 4 plus 5 plus 6, this is going to be, and divided by 6, so this is going to be 3.5. Okay, 3.5, so which is the theoretical value. And if, let's say, we continue rolling a dice, and we roll it n times, theoretically n over 6 times we should get 1, n over 6 times we should get 2, n over 6 times we should get 3, and so on and so forth. Okay, so then we add them up. So we take 1 multiplied by 1 by n divided by 6, then we take 2 multiplied by n divided by 6, and so on and so forth, and then divided by n. Okay, so divided by n. Yeah, n cancels out, and again we have the same thing, like 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, which is going to be 3.5 if you calculate it. Okay, so this is just the average value of the values which we roll. Okay, so that's not something we see in average, yeah, because we are not going to see 3.5 and 3.6 like on the side of the die. Yeah, so this is just the average value. So this is mathematical. This is mathematical characteristic of this process. One of like the statistical characteristics of this process. Yeah, measure of the center. And it is also called expected value, and it also used in a whole bunch of other applications, for example, in the game theory. Okay, so the variance. So variance, let's use that shortcut formula, and we'll use the sum product. X squared, so let's grab x and square it. And then we have our probabilities again here. And then we have minus mean squared. Okay. Okay, and again, like we can go ahead and use the brush. Right there, this is our variance, and variance is standard deviation squared. That means that the standard deviation is equal to square root of variance. Okay, and if again we format, it's 1.7. So see this value there, 1.7. Okay, so then here we just need to calculate the probabilities of rolling 2 or 3 or 4 or 5. Yeah, we just need to add up those probabilities. Equal to sum, and those are probabilities from 2 to 5. Okay. Done. Okay, yeah, we can maybe format it slightly differently. Yeah, that looks good. 0.7, reasonable. Okay, so then theoretical values. If you calculate theoretical values, mean is equal to it's some product, and those are our x's and the probabilities. Now it's theoretical probabilities right there. And you see it's exactly 3.5 as we predicted. And they're slightly different. But again, if we roll our die many times, as you can see here, that's the illustration. Our experimental value of mean is going to approach theoretical. Okay, so the variance again, we will use the same shortcut formula. Some product, and those are our x squared, and then those are theoretical probabilities. Yeah, and then minus mean squared. Okay, and yeah, let's maybe again format it the same way. Okay, standard deviation, so that's the square root of variance. Okay, so quite close. See, quite close. Yeah. So within that, accuracy is even the same. Yeah, and again here we calculate probabilities from 2 to 5. We sum those probabilities from 2 to 5. Okay, 0.67. Yeah, so again, quite close to this one. And again, like according to the law of large numbers, yeah, if we roll it more, yeah, these values will approach these values. Okay, so I think we should be good with this introduction. So now let's go ahead and analyze a data set which is quite similar to what you have in your lab. Okay, let's say we are testing 5,000 parts, yeah, and check how many defects we have. Okay, so here we were rolling a die, so here we take 5,000 parts and check them for defects. And let's say here we got 59, here we have 54, and so on and so forth. Yeah, the definition of probability which we are going to use is this one. That's number of times A occurred divided by number of times procedure was repeated. So let's see how many times procedure was repeated. So that's number of times procedure was repeated. Okay, we will just count everything here. 460 times. Yeah, let's calculate minimum number of the defects. So this is minimum. And let's calculate the maximum. Okay, 100. So we have amount of defects from 1 to 100. Okay, so let's introduce our random variable, and our random variable in this case is going to be just the amount of defects we get once we test 5,000 parts each time. Okay, so we will go ahead and do 1. So this is equal to this plus 1. Yeah, and then we drop it down to too much, to 101. Yeah, that's it. 100 and 101. A couple of times. Yeah. Okay. So that's what we have. So let's maybe center everything. The frequencies. So how many times that happens? So how many times that happens? So how many times we take 5,000 parts, yeah, and get just one defect? Yeah. So we are going to use countif function, count if, and our range. So that's this data right there, and criteria search. How many times we have? 1. Go for it. 3 times. Yeah, that happens 3 times. So if you drop down, so now you see it's fixing like that range, yeah, and then flips like to the moves to the next point here. Okay, yeah, and we can double click here. That's what we have. Yeah, that's what we have. Those are our frequencies. Okay. Here we have 8 defects, so 7 times. So 7 times we tested 5,000 parts and got 8 defects among like those 5,000 parts. Okay, so then we can calculate probabilities. In this case, this is going to be number of times A occurred. It's equal to number of times A occurred divided by total number of times procedure was repeated. So we can put 460, or we can go ahead, grab this one and fix it. Yeah, fix it. Okay, so then we drop down and done. Yeah. We are ready to go, yeah, to calculate our mean, variance, and standard deviation, and some cumulative probability right here. Okay, so mean, we are going to use formula for mean. So again, we will use some product, and those are our x's. So those are v2 to v101. Yeah, we can check that if you're selecting everything. So see, it's 100, perfect. Yeah, since we are shifted by 1, yeah, so then it's going to be to 101. Okay. And here we have probabilities. They go from x2 to x101. good. So that's our mean. Okay. Then we can calculate the variance using our shortcut formula. So some product of our axis. So again, we go from V2 to V101. Okay, and this is squared and multiplied by our probabilities from x2 to x101. Okay, and then minus mean squared. Perfect. Okay, then standard deviation is just a square root of that. Okay, and this is just going to be the sum, and we go from 23, it's right there, 23, and we go to x, what is this, 47, so we go to 48, that's in there. Okay, we can go ahead and check just in case. So see here 47, so from 23 to 47. Okay, and done. Yeah, so about 24% of this to happen. What is this? Yeah, so this is if we keep checking 5,000 parts. So what is the probability to get 23 defects or 24 defects or 25 and so on and so forth up to 47. Okay. Yeah, that's what you need to do in your lab number 3 in the first part. Again, guys, I'm going to record the video related to Poisson distribution in the next couple of days, and this should be enough for you to do the first part of the lab. Okay, so I hope this helps, and good luck.